Section 12.3, Double Integrals and Polar Coordinates, Video 7. To conclude this series, we're going to look at one more example. We're going to find the volume of the solid that lies underneath a paraboloid, defined by z equals x squared plus y squared, bounded above by the xy plane. Above the xy plane, not bounded above by the xy plane. And is inside the cylinder x squared plus y squared equals 2x. This is a little tricky one to wrap your mind around visually because of the solids and the surfaces that we're looking at in 3 dimensions. So let's start by looking at what the paraboloid would look like. In the in the YZ plane, and then we'll bring in the x-axis. To see what the trace looks like in the YZ plane, we have to pretend x equals 0. Well, if x equals 0, we have z equals y squared. That's just a standard parabola. If we bring in the x-axis, then in the xz plane, we would let y equal 0, and we would just have another parabola. So if I open up a parabola here, and go ahead and draw these circles, then we would have a paraboloid that looks a little something like that. Okay. Now, let me do this to give us some depth. Okay. Now, we're looking for the volume of the solid that's underneath this, not inside of it. But it's also bounded, it's also above the xy plane, so we're only looking above the floor, if you will. But it's also inside the cylinder. Now, why would that be a cylinder? Well, first off, notice it doesn't have any z-coordinate, which means whatever shape it is on the xy plane is the same shape up in, anywhere, moving up or down, regardless of what z is. So we really just have to figure out what this looks like in the xy plane, and then take its projection up and down, and it will create a cylinder. In case you haven't figured out, it's going to be a circle. But what circle is this? Well, we would have to complete the square. If we move the 2x over and put the minus 2x after the x squared term, we have x squared minus 2x plus y squared equals, 0. Getting ahead of myself. To complete the square on the 2x terms, we would have to square half of -2. So half of -2 is -1. -1 squared is +1. I need a +1 after the first 2x terms. But if I add 1 to the left side, I have to add it to the right side. And now this trinomial factors into a perfect square into x minus 1 squared. And so that equation is equivalent to x minus 1 quantity squared plus y squared equals 1. Well, that's just a circle. It's a circle whose center is 1, 0, and whose radius is 1. So let's pull the xy plane out just for a moment. It's always a good idea when you're doing a double integral over a region to pull out the plane in which that region lives, in this case the xy plane. So we have a center at 1, 0, and a radius of 1, which means it will go right through the origin, up 1, to the right 1, and down 1. Now, let's see if we can sketch this inside this 3-dimensional picture. If I take this circle in the xy plane and put it where it belongs, which is on the positive part of the x-axis, so it would belong over here. And then shoot it straight up. I'm going to make it a little bit smaller so it actually hits the paraboloid. There we go. And then shoot it straight up. It's going to hit this paraboloid, and then there's going to be the solid that is under the paraboloid and above that circle. Okay, that just looks like a big hot mess. There's a fairly decent picture of it on page 713, a little bit better than I could draw, but we're looking for the volume of the solid above this circle in the xy plane and below this paraboloid. So it's another just integrate this equation with the correct limits of integration. But what would the correct limits of integration be? Well, if we think of this in terms of rectangular coordinates and set up a representative rectangle oriented vertically, then the x's would this rectangle would just slide between 0 and 2. But the problem isn't what's defining the left and right bounds of the rectangle. The problem is what's defining the upper and lower bounds. The top of this rectangle is defined by this equation, and the bottom of this rectangle is defined by this equation. So if we were doing this in rectangular coordinates, we would have to solve this equation for y, which isn't that hard. Move the x squared over and square root it. The positive square root would be the top bound, the negative square root would be the negative bound. Those would be our limits of integration. Things would get ugly, if not impossible. By the way, there are integrals that you cannot do. If you needed their value as a definite integral, you could take numerical approaches to estimate their values. But I digress. I think this would be a little easier to attack in terms of rectangular coordinates, but if we're going to attack this in, polar coordinates, but if we're going to attack it in terms of polar coordinates, we need to know what's the equation of this region in the xy plane in polar coordinates, and what would the bounds be for the limits of integration. Well, in order to get the equation in polar coordinates, let's go back to the equation in rectangular coordinates. X squared plus y squared equals 2x. We have equations that will convert this for us. X squared plus y squared is just equal to r squared. X by itself is r cosine theta. Now, most of the time, you shouldn't divide by a variable to cancel it, but we're going to divide by r here. Because the only time dividing by a variable is a bad idea is when that variable could be 0. When r equals 0, that means you're at the origin. If we divide both sides by r, we get r equals 2 cosine theta. Is it possible to still be at the origin in this equation? In other words, is there a value for theta that we can substitute that would give us r is equal to 0? Sure, there's a lot of them. Pi over 2 is one of them. Negative pi over 2 is another. So by dividing both sides by r, we don't lose the point on the graph where r could be equal to 0, which is at the origin, because we can still recover that point by letting theta be the correct angle. So that's the equation of our circle. But what would our limits of integration be? Well, this is where you have to think about sweeping out an angle along here. If our angle was 0 radians, then we would be going straight out here, and we would hit the circle over there. What's the greatest angle we can rotate and still hit the circle? Is it pi over 4, 45 degrees? Well, we would hit the circle there. Is it 60 degrees? Pi over 3. Is it some other radian that's larger? Well, in theory, we can rotate a ray all the way up to pi over 2 radians and still be on the circle. In fact, if you think about it, as we rotate, the radius is getting smaller and smaller, and when we finally hit pi over 2, our radius is 0. So yeah, we can rotate this all the way up to an angle of pi over 2. But what about on the other end? If we start out at 0 radians and rotate backwards, we're still hitting the circle all the way until we hit negative pi over 2, in which case the radius collapses down to 0. So we can set the lower bound for the circle as negative pi over 2. But what would the radius be bound by? Well, the radius is bound by the equation of the circle. So our radius is always going to be greater than or equal to 0. But no matter what our angle is, the radius ends when I hit this point on the circle, and that circle is defined by r equals 2 cosine theta. So in other words, my outer radius is defined by this equation, 2 cosine theta. It's a little tricky to set up the limits of integration in polar coordinates when they're not constants, but just ask yourself, what angles can I sweep out and still be on the circle? And as I'm rotating, how far out is the radius going? It's going all the way out to this graph, whose equation is defined by r equals 2 cosine theta. All right, let's set up the integral. We're going to set up the integral over this region, which I never call r, but there it is. And the function below which we're integrating is z equals x squared plus y squared, dA. All right, let's turn everything into polar. Let's start with the integrand, x squared plus y squared. Wait, that's just r squared. The dA becomes r dr d theta. Don't forget the r. Our radius is bound below by 0, but bounded above by the equation r equals 2 cosine theta. And our angles are bounded between negative pi over 2 and pi over 2. The hardest part of this problem is done. Let's focus on the inner integral, and then we'll import the results into the outer integral. The inner integral is the integral from 0 to 2 cosine theta of r to the 3rd power dr. That's just 1/4 r to the 4th power evaluated from 0, oh this is going to get fun, to 2 cosine theta. So if we substitute 2 cosine theta in, the 2 gets raised to the 4th power, that's 16. 1/4 of 16 is 4. The cosine gets raised to the 4th power. So there's the substitution of the upper limit of integration. If we substitute the lower limit of integration, we just get 0. So there's the results of the inner integral, 4 cosine to the 4th power theta. Now all we have to do is import that back into the outer integral and integrate it. I think I'm going to pause the video, clear out some space, and then we'll finish.